Assalamualaikum dear students. Today we are going to discuss a few more examples of uniform continuity. In last lecture I have discussed the definition of uniform continuity, and we have observed the difference between the definition of a continuous function and a uniform continuous function. Right. So here is one more example. Fx is equal to x square on 0b, whatever b is uniformly continuous. It's a closed interval. So if for epsilon positive we choose delta, so I am leaving here delta because we have to decide ultimately that how much delta we may choose to satisfy the definition of uniform continuity, such that if x minus y mod is less than delta, then fx minus fy mod, and what is this? This is equal to x square minus y square, and you have seen that this is equal to x plus y into x minus y, which is equal to x plus y mod and x minus y mod, right? And from here this is x minus y mod is less than delta, so this is in fact x plus y mod into delta. And this further, you know that x plus y mod is less or equal to x mod plus y mod, and this is in fact less or equal to x mod plus y mod into delta. So I can write like this. I can write fx minus fy mod is equal to is less than x mod plus y mod into delta. Okay, so now you know that here x and y both belong to 0b, and that's why this x mod must be less or equal to b, and similarly this y mod must be less or equal to b, right? So here I can write that this is less or equal to b plus b into delta. So our fx minus fy mod is less or equal to 2b delta. Now you know, if you choose delta is equal to epsilon by 2b, right? So for epsilon positive we choose delta is equal to epsilon by 2b, or delta is lesser than epsilon by 2b, then you can see the definition. That definition would ultimately be satisfied. So here that's why I left delta, that what is the value of delta. The through calculation you can decide later that what should be the value of delta. So here for epsilon positive choose delta is equal to epsilon by 2b, or delta is lesser than epsilon by 2b. So here you see that delta is depending upon epsilon only, because b is your fixed number. B is not your arbitrary point, b is your fixed number. It's a closed interval. B is a real number. It could be 0 to 10, 0 to 20, 0 to 100, whatever you are choosing. So here this b is in fact 0 to 100. So if here is 100, then in fact you are choosing that delta is equal to epsilon by 200. This is 2b. Delta is equal to epsilon by 200. So that's why delta is free from point. So we are not using point by choosing the value of delta to satisfy the definition of uniform continuity. So that's why this is equal to 2b into epsilon by 2b whenever x minus y mod is less than delta. So now this is the definition. You can see that we have evaluated. So what does it mean? That our fx minus fy mod is less than epsilon whenever x minus y mod is less than delta for all x, y belong to 0, b. Okay, look at the definition. Now our definition of uniform continuity is clearly satisfied. So we have decided delta, and after finding this, it is so easy to see that if you choose delta is equal to epsilon by 2b, then there must be this 2b would be cancelled, and this must be lesser than epsilon. So whenever x minus y is less than delta, so here delta is equal to epsilon by 2b, or you can say delta is less or equal to epsilon by 2b, whatever you want to choose, you can, right? So why this was happening? Because both x and y belong to 0b closed interval. That's why this x mod must be less or equal, because x is any number of this, and b is in fact the maximum of this domain, right? So x mod must be less or equal to b, and similarly y mod is less or equal to b, right? So therefore the definition of uniform continuity, by using the fact that this is less or equal to b plus 2b delta, and then by choosing delta is equal to epsilon by 2b, you are getting that fx minus fy mod is less than epsilon whenever x minus y mod is less than delta for all x, y belong to 0b closed interval. That's why I can say that fx is equal to x square on this closed interval is uniformly continuous. Hence fx is equal to x square on 0b is uniformly continuous, right? Okay, next example is if you choose any linear function on real line, then it would be uniformly continuous. Okay, next example is fx is equal to whatever you want to choose, that is 3x plus 2, or in general you can choose ax plus b, it's a linear function, linear line, on is uniformly continuous on R, right? Once again, you choose delta, and later we will decide that what should be the value of delta, so that the definition of uniform continuity is satisfied. So here for epsilon positive, we choose delta is equal to what? I am leaving the step, because after finding the calculation, I will decide that what should be the value of delta here, so that we can see the exact definition of uniform continuity. It's not a problem, right? So that if x minus y mod is less than delta, then you have to check that fx minus fy mod, you know x and y are arbitrary point, so you need to show that this is less than epsilon for some appropriate value of delta, depending upon epsilon only, not depending upon the point, right? So fx minus fy, from here this is 3x plus 2 minus 3x minus 2, yes, this is equal to 3 times x this is y, x minus y, and you know that x minus y is less than delta. This is in fact 3 delta, and if you choose delta is equal to epsilon by 3, so delta is equal to epsilon by 3, or delta is equal to, delta is less than epsilon by 3, then this will solve, right? And 3 delta, from here 3 delta is equal to epsilon, so this is equal to here whenever x minus y mod is less than delta, or you can say that, what is this? This is equal to epsilon, or fx minus fy mod is less than epsilon whenever x minus y mod is less than delta. Okay, you see the definition of uniform continuity is clearly satisfied. That's why I insert the value of delta after finding the calculation, so that I can see the exact definition of uniform continuity. Right, so you can say that this function is uniformly continuous on the entire set of real number, whereas the function fx is equal to x here was not uniformly continuous, as you have seen in my last lecture, right? However, fx is equal to x square is uniformly continuous on a closed interval 0b. That's why you can say that a function may be uniformly continuous or may not be uniformly continuous on a similar domain with respect to, on a set with respect to your domain. So, you know that when we have changed domain 0b instead of the entire real numbers, it was uniformly continuous. However, fx equal to x square was not uniformly continuous on the entire set of real numbers. But here, this is the function. As we have seen in my last lecture graphically, that straight line was the ideal graph to understand the definition of uniform continuity, because you can take a slide on that graph without any jumping, right? There are no jumps, no sharp jumps like in the definition of uniform continuity, so that the chance of changing delta values are not possible, right? So that's why this is the straight line, you know, this is the graph of straight line, is obviously uniformly continuous. However, you can see with the help of this process as well. Okay, next idea is, if f is uniformly continuous, okay, I have a little theorem. If f is uniformly continuous on I, so theorem, if f is uniformly continuous on I, where I is an interval, then f is continuous on I. Then f is continuous on I. But converse may not be true. But converse may not be true in journal. Okay, since every uniformly continuous function is continuous, and a continuous function may not be uniformly continuous, that's why you have a quest. We must have to know that which type of functions are always uniformly continuous whenever they are continuous, because we are classifying continuous function into two classes. One class where functions are continuous but not uniformly continuous, and the other class is functions are continuous and they are uniformly continuous as well. That's why you must have to know that. Can you find all those functions which are continuous? Then they must be uniformly continuous as well. So therefore, you have a continuity theorem like the previous example. So if f is continuous on a compact set, I mean to say that in real line, you know that a closed and bounded set is called a compact set. So if f is continuous on a closed and bounded set, then it must be uniformly continuous. That is also known as uniform continuity theorem. Okay, so this is the first idea that clearly asserts that not every continuous function is uniformly continuous. So, but if it is uniformly continuous, then of course your definition of fx minus fy mod is less than epsilon whenever x minus y mod is less than delta is always satisfied for epsilon positive. We choose delta positive such that fx delta is depending upon epsilon. Delta is, you can say that delta depending upon epsilon naught and is positive. So that fx minus fy mod is less than epsilon whenever x minus y mod less than delta for all x, y belong to your domain I. So when your function is continuous, then it is obviously, when your function is uniformly continuous, this is obviously continuous. So you just substitute y x naught instead of y. So if we put y is equal to x naught, then you see that fx minus fx naught mod less than epsilon whenever x minus x naught mod less than delta. So from here like this you can see that fx minus fx naught mod is less than epsilon whenever x minus x naught mod is less than delta. So see, this is the definition of continuity at a point x naught. Since y was the arbitrary point, so that's why this function is continuous at all such x naught. That's why it is continuous. So if a function is uniformly continuous, then it is obvious that this function is continuous as well. However, a continuous function may not be uniformly continuous. So let's have another example. So take, let fx is equal to 1 over x on 0, 1. If you choose this function, if you take this function, fx is equal to 1 over x, then obviously this function is continuous on 0, 1. Clearly, f is continuous on 0, 1. You know that function is defined at all points of the domain. Here 0 is not the point of this domain. So this function clearly continuous. But by choosing some points from this interval, I can show that this function is not uniformly continuous. Okay. So for this, let epsilon is equal to 1 by 2 positive. Choose delta positive and a natural number n such that 1 over n is less than delta. Okay, this is possible because this is the natural number, and if you take a larger natural number, so 1 over n must be less than delta, whatever delta you are choosing, however small you are choosing. You fix the value of delta, you can always find a natural number. So that 1 over n must be less than that. Also this can be proved by using the Archimedean property of real numbers, right? So if we choose a natural number such that 1 over n is less than delta and your epsilon is equal to 1 by 2, and take 2 points, we take 2 points, x is equal to 1 over n and y is equal to 1 over n plus 1, then we see that then x minus y mod is equal to 1 over n minus 1 over n plus 1. This is equal to, you can simplify this, n plus 1 minus n over n into n plus 1, and you know this is equal to 1 over n into n plus 1. You know this is less than 1 over n because n into n plus 1 is greater than n. So 1 over n into n plus 1 is lesser than 1 over n plus 1. This is very simple. It's very simple. N into n plus 1 is greater than n. So this implies 1 over n into n plus 1 is less than 1 over n. But this 1 over n is less than delta. So you see that you have chosen a delta in such a way that x minus y is less than delta, where delta is arbitrary and of course a small positive number. Since this is always possible, you can find a natural number so that 1 over n is lesser than delta, and also 1 over n belong to this interval, right? So these 2 points x and y, if you take x is equal to 1 over n, y is equal to 1 over n plus 1, then x, y belong to 0, 1. There is no doubt. So I have chosen 2 numbers from this interval 0, 1, so that x is equal to 1 over n and y is equal to 1 over n plus 1, with the condition that x minus y mod is less than delta. But I need to check whether fx minus fy mod is less than epsilon. If this is not the case, whatever the way I am choosing, we are not concerned. But if I can find any 2 points which through which I can contradict the definition of uniform continuity, then of course in general it would not be uniformly continuous. Okay, so I have chosen these 2 points. One is 1 over n and the other is 1 over n plus 1, and you have seen that x minus y mod is less than delta. But what is the value of fx minus fy? Where but fx minus fy mod, this is equal to what was fx. So fx would be 1 over n because fx was 1 over x. So this would be equal to 1 over n, 1 over n minus 1 over this was n plus 1, 1 over n plus 1, right? And this is equal to, you know, this is equal to n minus n plus 1, and this is equal to, in fact, minus 1 mod. This is equal to 1, which is greater than 1 by 2. That was the epsilon. So you have chosen epsilon is equal to 1 by 2. So you see that fx minus fy mod is greater than epsilon even though x minus y mod is less than delta. So this is in fact against the definition of uniform continuity. Hence this function is not uniformly continuous on 0, 1. However, it is continuous on 0, 1 interval, open interval. So that's why we can say that a continuous function may not be uniformly continuous. That's why you have a quest. Now you need to know that which type of functions, which type of continuous function must be uniformly continuous. And that's why you have a theorem, and this theorem is known as uniform continuity theorem, in which we state that if a function f is continuous on a closed and bounded interval, then it would be uniformly continuous. It's a very popular result. Okay. So I have another example. You can say that hence fx 1 over x is not uniformly constant. But there is another example. Fx is equal to 1 over x on a infinity is uniformly continuous. You see, I have the same function. This is the same function 1 over x, but I have changed the domain a to infinity. This function is uniformly continuous on a infinity. Okay. So now you have to show in general the definition of uniform continuity. So let xy belong to a infinity, then x mod must be greater than a and y mod must be greater than a, or you can say that 1 over x mod is less than 1 over a and 1 over y mod must be less than 1 over a. We will use the fact. Since xy belong to this interval and this interval is starting from a to infinity, therefore x mod must be greater than a and y mod must be greater than a. That's why 1 over x mod and 1 over y mod must be less than 1 over a. Now we will use these relations, right? So for epsilon positive, choose delta is equal to what? Now I am leaving the step because after finding fx minus fy, I have to decide that how much delta value I should choose so that the definition of continuity is satisfied. Right. Delta is equal to such that if x minus y mod is less than delta, then fx minus fy mod, this is equal to 1 over x minus 1 over y, right? You know fx is equal to 1 over x, and if you simplify, this is equal to y minus x over x, y mod, and this further can be written as x minus y mod over x mod y mod. You know 1 over x mod is less than 1 over a and 1 over y mod is less than 1 over a. So you can write this is less than 1 over a square x minus y mod, and you know that x minus y mod is less than delta. So fx minus fy mod is less than 1 over a square delta whenever x minus y mod is less than delta. Now if you choose delta is equal to delta by a square is equal to epsilon. So if you choose this, so delta is equal to a square epsilon, then again you see that delta is depending on epsilon, not on the point, because a is the starting point. This is not in fact the arbitrary point. This could be 1 to infinity, 2 to infinity, 3 to infinity. So a could be 1, 2, 3, 0.1, 2 square root, 3 square root, whatever you are choosing. Like if you are taking interval this 2 square root to infinity, then a square would be 2. So delta would be 2 epsilon. So delta is depending upon epsilon only, not on the point x or y, right? So that's why the definition would be satisfied. This would be equal to epsilon, right? So what does it mean? This means that fx minus fy mod is less than epsilon whenever x minus y mod is less than delta. Yes, this definition is satisfied for all x, y belong to 0, 1. Because I have chosen x and y arbitrary points from this interval, and since x and y belong to this, so x mod must be greater than a, y mod must be greater than a, so that 1 over x mod and 1 over y both must be less than 1 over a. And then if x minus y mod less than delta, for this delta values, then fx minus fy mod must be less than 1 over a square x minus y mod, which is less than delta by a square. So if I choose delta is equal to a square epsilon or delta by a square is equal to epsilon, then my condition of continuity, this uniform continuity, would be satisfied, where delta is not depending upon any value y. So any point, arbitrary point of this interval, rather it is a, we are using a. So that's why you can say that in general this function is uniformly continuous. But in previous example I have shown that this function was not uniformly continuous on 0, 1. However, this is uniformly continuous on a infinity. So that's why a function may be uniformly continuous and the same function may not be uniformly continuous depending upon your domain. So you can never say without domain that this function is uniformly continuous, right? However, your line, straight line, that was the ideal example as I have elaborated in my last lecture. This function is uniformly continuous on the entire R, so because it would be uniformly continuous on every subdomain as well. Right. Now there is another example. Let fx is equal to x square root on 0 infinity, then f is uniformly continuous. Okay, again for epsilon positive we choose delta is equal to, I am leaving this space. After finding the calculation, I'll write delta is equal to what, so that the definition is satisfied. So choose such that if x minus y mod is less than delta, then f x minus fy mod this is equal to x square root minus y square root, and this is less or equal to x minus y, I think, square root mod. This is a well-known result. You can see from some calculus books that this is equal to x minus y mod, or this, because I'm not saying that whether x is larger or y is larger, that was if x was larger. So that's why you write here and take absolute shares. So this is less than delta square root. This is less than delta square root. And if I write this is equal to epsilon, whenever x minus y mod is less than delta, so what I should choose? I should choose delta square is equal to epsilon, so that delta is square is equal to epsilon. Choose delta positive, here you choose delta positive with delta square is equal to epsilon, such that if x minus y, so here delta is positive, emphasizing the concept because epsilon is positive. From here you can write delta square is equal to epsilon. Also it is a square value, it must be positive. No need to write this. So we choose delta square is equal to epsilon, so that whenever x minus y mod less than delta, then fx minus f by mod is equal to x square root minus y square root, which is must be less than equal to x minus y mod square root. You can verify this result. Okay. So from here this is less than delta square, because I'm choosing this is less than delta square root. So delta square root means delta square root is equal to epsilon square, or delta square is equal to epsilon. So here whenever x minus mod is less than delta, hence fx is equal to x square root on this interval 0 infinity is uniformly continuous, right? So write another example. You see, we have another example. Fx is equal to x power n is uniformly continuous on the closed interval on 0, 1 where n is greater than or equal to 0. This is the polynomial function of degree n, and this function is also uniformly continuous on this domain 0, 1. It is so easy to show that this is uniformly continuous. So for epsilon positive, choose delta is equal to what? I am leaving this step such that if x minus y mod is less than delta, then fx minus fy mod, you know what is fx? This is equal to xn minus yn, and you know that this is equal to x minus y into xn plus xn minus 1y plus xn minus 2y square plus so on plus x y n minus 1, right? This is equal to n minus 1. This is equal to n minus 2. This is n minus 3, right? This one. Oh, this is very simple. You can check this by using the simple division. If I divide x minus y, if I xn minus yn, if I divide by x minus y, okay, we need x power n minus 1. So multiply here. This is x power n minus x power n minus 1 y, right? These are cancelled. This is here xn minus 1 y minus yn. Then again multiply by plus xn minus 2 and y, right? So if you multiply this number by again x, this is equal to xn minus 1 y minus xn minus 2 y square, right? Plus minus is cancel and so forth. You will get the answer. So it's a very well known result. You can prove this. Xn minus y is equal to x minus y into xn minus 1 plus xn minus 1 y, xn minus 3 y square, and so on, x y n minus 1. And further, this is equal to x minus 1 mod, that xn minus 1 plus xn minus 2 y plus so on plus x y n minus 1 mod. Okay, you know this is less than delta. This is less than delta, and this one is less than delta, and here you can use the triangular inequality. This is less or equal to xn minus 1 mod, xn plus xn minus 2 mod, y mod plus so on plus x mod yn minus 1 mod, like this. You know, each of the number belong to 0, 1. So that's why this must be less than 1. 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 So if you substitute the maximum value, that is 1 of this interval, because all are the points x and y are the points of this interval, so that this x power n minus 1 can be written as x power n minus 1. You can write here, this further can be written as fx minus fy mod is less than delta, and this can be written as x mod power n minus 1 plus this is x mod power n minus 2 and y mod plus so on plus this is x mod, this is y mod power n minus 1. Now, if I use the maximum value, of course, whenever x minus y mod is less than delta. Now, if I use the maximum value, because x belongs to this interval, so its maximum value is 1. So instead of this, I put 1. This is 1, this is 1, and so on. If I use 1, this must be less than delta time 1 plus 1 plus 1 plus so on plus 1. These are in fact n values, because here y power 0 and here y mod power n minus 1. So from here to there, these are the n minus 1 values, and here y mod power 0. So these are n values in number. So this is in fact n terms. N terms. Right? So this implies that fx minus fy mod must be less than n delta whenever x minus y mod is less than delta. Now, if I choose this n delta is equal to epsilon, this will serve that this delta is depending upon epsilon only, but not n, because n is the natural number. N is the natural number. It could be 2, 3, whatever the terms are here. Okay. So here n is the natural number, is greater than or equal to 0. So this is not some arbitrary point of this interval. So that's why if you for epsilon positive choose delta is equal to epsilon by n. Yes. If I choose delta is equal to epsilon by n, that is n delta is equal to epsilon. So this means that this implies fx minus fy mod is less than epsilon whenever x minus y mod is less than delta for all x, y belong to 0, 1 closed interval. Hence, this function is uniformly continuous. This means that this polynomial function is uniformly continuous on this closed interval 0, 1. And you know that every polynomial function is continuous on a closed interval, and I already told you that yes, we have some continuous functions which are not uniformly continuous, so that we need to know that which continuous function must be uniformly continuous. And we have seen that if your function is continuous on a closed and bounded interval, then it would be uniformly continuous. Like all polynomial functions are continuous on this closed interval, so because this polynomial function must be uniformly continuous, as I have shown through this example. Right? Okay. Next is the uniform continuity theorem. The last one is okay, thank you very much. Next time we will discuss uniform continuity theorem and few other theorems to discuss some popular results of uniform continuity. Thank you very much. Allah Hafiz.